China's teasing hints about the groundbreaking nickel-63 nuclear battery has once again captured the attentions of alternative energy enthusiasts, poised for potential commercial release in the not-so-distant future. On one hand, without a doubt this technology will be revolutionary, that is, if China's news is true. On the other hand, nuclear batteries are nothing new, and in this video, we will discuss how the technology works, and more importantly, its revolutionary aspects, as well as the dangers it poses for the future of humanity. A Chinese startup named Betavolt recently announced that their new and revolutionary nickel-63 nuclear battery will be commercially available sometime in the near future. They promise 50+ years of battery life and no radiation issues. Images provided by the company depict a tiny battery no bigger than a nickel. If true, this product has the potential to revolutionize many industries, but not without controversies, such as how much power can it actually generate? Is nickel-63 production realistic? What about radiation? And lastly, a battery that lasts 50+ years would be better or worse for the environment. While Betavolt product may sound new and revolutionary, the idea of diamond batteries isn't new. In 2018, a study conducted by the Moscow Institute of Physics and Technology, among other institutes, announced a prototype using a 2-micron thick layer of nickel-63 sandwiched between 210-micron diamond converters, producing a total power output of 1 microwatt, or a power density of 10 microwatts per cubic centimeter. Considering those values, the energy density would be approximately 3.3 watts per gram. The working principle is quite simple. During nickel-63 radioactive decay, it emits beta particles, which are essentially high-energy electrons. These beta particles interact with the diamond lattice, effectively creating a gradient of electrons where one side gains electrons and the other side loses. This separation of charges creates an electric potential, leading to the flow of electric current through the diamond semiconductor. As long as the decay happens, the current on the diamonds persists. However, while on paper everything checks out, just like with any new technology, nuclear batteries face a steep uphill battle from research and development to market. First off, nickel-63 is only available through laboratory synthesis, where nickel-62 is bombarded with neutrons. As you may expect, this process is complex and expensive. As with any new technology, the complexity of nickel-63 production is what makes this news sort of bogus. Nickel-63 is used in some smoke detectors, however, the quantity is extremely small, in the nanograms, which isn't enough to do anything besides detect smoke. Second, the diamond lattice for the battery needs to be free of defects, something that only synthetic diamonds can achieve. Luckily, synthetic diamonds are inexpensive, however, production scalability is uncertain. Of course, everything is in early stages of development, so questioning production scalability may be unfair at this point, but logically, everything points that way. What we know for certain is that this technology will be part of humanity's future regardless of personal opinion. While nickel-63 may never happen, one other isotope may be in the horizon, and that is carbon-14, which I will talk more about it later. But what about radioactivity? Beta decay isn't as harmful as gamma radiation and can only travel short distances when unshielded. If shielded with plastic, it can only travel a few millimeters. Of course, that all depends on how powerful the radioactive source is. Considering nickel-63 or carbon-14, minimal shielding is necessary. This is good news for batteries, as they can be much lighter when compared to lithium-ion ones. But when does radiation becomes a problem though? Well, to power anything meaningful, lots of these batteries are necessary, thousands, if not more, to power a car, for instance. If built properly, being leak-proof with some of the newer plastic and fiber technologies, in any scenario, these batteries can be revolutionary. However, we always have to consider unforeseen scenarios. For certain, there are markets that could benefit immensely from nuclear batteries. Two such markets are the automotive and aviation industry. Initial studies suggest that diamond batteries can output 10 times more energy than current batteries. In practice, what that means is that they offer unlimited driving range in a package 1/10 the volume of any electric car today. In other words, if we consider these numbers at face value, Compared to lithium-ion batteries at present, which hold specific power in between 250 and 340 watts per kilogram, nuclear batteries contain about 3,300 watts per kilogram. The catch is, lithium-ion batteries need to be charged, while nuclear lasts forever. So, at the end of the day, not only your car will be lighter, but it will break many times before you run out of battery power. For the aviation sector, with its substantial fuel and energy expenses being 20 to 40% of all operation costs, nuclear batteries could be the holy grail. These compact and powerful energy sources offer solutions to the industry's perpetual goals of enhancing fuel efficiency and extending aircraft range. Mind you that all planes would have to be electric. The continuous and long-lasting power supply from nuclear batteries completely removes fuel dependency, resulting in substantial cost savings and extending flight ranges. Additionally, the compact nature of nuclear batteries allow for a reduction in aircraft weight and the elimination of large fuel tanks, potentially leading to lighter planes with increased payload capacities. This shift could translate into improved efficiency, zero emissions, and enhanced overall performance. Considering the growing environmental scrutiny faced by both industries, nuclear batteries offer a cleaner alternative to conventional fuels. While initial investments may pose challenges, the long-term cost savings could create a more economical and sustainable model for everything, really. On the other hand, the revolutionary concept of nuclear batteries, with the potential to power devices for decades, raises moral and safety concerns. While shielding can completely stop radiation risks, the idea of devices, including cars and aircrafts, being fueled by such long-lasting batteries poses significant challenges involving safety, long-term impact, and technological dependency. However, the most challenging aspect is, of course, safety. Can we really assure consumers that in the event of an accident, there won't be any radiation leaks? There are numerous plastics and fibers that can survive extreme accidents without a scratch, but that means that companies producing such batteries will be under tight regulation and quality control, something that is really hard to keep up with over the years. And don't forget that all it takes to make things worse is just one accident with faulty batteries for everything to go down the drain. Though radiation sounds scary, and it is to some extent, depending on the source, I wouldn't want to be near a plutonium battery, for instance, if it leaks. The best option for nuclear batteries would be carbon-14. With a half-life of 5,700 years, forget about long-term impacts, as these batteries would be used and reused forever, basically. Now, radiation leaks are a real concern. Though carbon-14 is found basically everywhere in small quantities, concentrating that much radioactive material in one spot does pose dangers. Nuclear batteries have transformative potential across diverse industries. While presenting exciting possibilities, careful consideration of safety, regulation, and moral implications is crucial. As research progresses, nuclear batteries promise to revolutionize various sectors, providing stable, long-lasting power sources for a wide range of applications, eventually contributing to technological advancements and sustainability across industries. What do you think? Revolutionary or dangerous idea?